but then when you say disk, are you talking about like a solid disk?
A solid disk, yeah, like
Okay.
this one.
Yeah. Because
This is a solid disk.
And then the hollow pipe would basically be like the ring.
Correct.
Okay.
Yeah. So this would be like a hollow pipe.
Correct.
Yeah. Okay, so take a look at the next one. So the next one, number 7. This one says, a hockey puck sliding on a smooth ice. Smooth meaning what?
Frictionless.
Frictionless. So it's traveling at 4 meters per second, and then it's going to go up a hill. Okay, and it says the top of the hill is 1 meter above the ground. Okay, so there it is. So it says, will the mass make it to the top of the hill? Does it have enough energy to make it to the top of the hill? So first of all, if the block were to get to the top of this hill, does everybody agree that it would possess some amount of potential energy?
Yes.
Okay, what would that potential energy be at the top of the hill? mgh. Does everybody agree?
Yes.
So we don't know the mass. So let's just write it in terms of m. So m, and what's g? 9.8, and what's the altitude? 1. So if it got to the top and it stopped, it would still have this much energy. 9.8 times whatever its mass is. Even if it just stopped at the top, when it got to the top, it would still have this much energy. So let's see how much energy I start with, and if that energy is any less than this, I won't be able to make it up the hill. If that amount of energy that I start with is more than this, then I will be able to make it up the hill. Okay, so let's see. So, does everybody agree that here I don't have any potential? Because where am I? On the ground, right? But I do have kinetic. So that's going to be 1/2 the mass times 4 squared. 1/2 mv squared. So that's going to be 4 squared is 16, divided by 2 is 8. So that's going to be 8 times the mass. Note that this is not meters here. This is times mass. So 8 times mass. So wait a second. I only have 8 times mass here and 9.8 times mass here. So let's just put a number there. Let's say the mass is 1 kilogram. So if I plug in 1 for n here, does everybody agree that that means I have 8 joules of energy? How much would I have even if I reached the top and I stopped? I would have 9.8 joules. Do I have enough energy to get to the top of that hill?
No.
I do not. Because it costs at least this much energy to get to the top. At least. That's if you stop. So if you got up to the top of the hill and you're still moving, there's more energy required for that. This is the energy cost to get to the top of the hill. Okay, which is also the amount of work that you would have to do to move a box and bring it from the ground up to the top of the hill. That's how much work would be required. But I only have this much, so I don't have enough energy to get to the top. So therefore, the top of the hill is a classically forbidden region for this object, for this particle. So that means it cannot actually be found at the top of the hill. So the answer is B, no. It does not reach the top of the hill. Okay, so 3 more conceptual questions. So take a look at problem number 8. Question number 8. So question number 8 has 3 balls. And they're launched in 3 different configurations, something like this. Now, would you agree with me that for sure in all 3 of those cases it's going to take a different amount of time to reach the ground? Would you agree?
Yes.
The least amount of time is going to be for this one. Does everybody agree? It's shot straight down. Or not straight down, but at an angle pointing towards the ground. This is going to be the next least time. This is going to be the most time. Because it has to go up first, and then it has to come back down, right? That's going to be the most time. But that's not what the question is asking. The question is asking, when they finally do land, how are their speeds related? Okay. So in order to answer this question, the first thing that I want you to notice is that they all start at the same altitude. Does everybody agree with that statement? They all begin at the exact same altitude. So would you agree with me that U initial is same for all of them? Would you agree? They all start off at the same altitude, so they start off with the same amount of potential energy. Okay, but it also tells me that they all are launched at the same speed. And since kinetic energy is 1/2 mass times speed squared, would you agree with me that initial kinetic energy for all of them is also the same? Does everybody agree? So therefore, if I sum the two, total energy is also the same. Does everybody agree that they all start off with the same amount of energy? Would you agree with that statement? They all start off with the same amount of energy. Okay, so now I can go to my final configuration in all cases. Do you agree with me that they all, when they finally hit the ground, they're all on the ground?
Yes.
So what would the final potential be in all of those cases?
The same.
Same, 0. So it's going to be 0 in all those cases. 0 joules. Okay. Now, kinetic final. So if we do this, let's take a look. U initial plus K initial equals U final plus K final. Does everybody agree U initial plus K initial is the same for all of those? So the left side I'm going to write same. Potential final is 0. So does everybody agree that that immediately says that kinetic final is the same? So if the kinetic final is the same in all three of those cases, since their masses are the same, because it said the balls were identical, that means that their masses are equal. So since the masses are equal, does everybody agree that that implies that the final speed is going to be the same in all three cases? Does everybody see that? And that is neglecting air resistance. Everybody agree that that would be without any air resistance whatsoever. So you can write kinetic final as 1/2 mass times V final squared. But since the mass is the same, this would imply that V final is the same in all cases. Okay, so the answer to this one would be all of the balls would have the same exact speed. So that would be D. All right, so take a look at problem or conceptual question number 9. So number 9, it says 2 boxes are sliding on a frictionless surface. So 1 kilogram traveling at 4 meters per second, another object of 2 kilograms traveling at 2 meters per second. Okay. What am I missing there before I proceed? I'm missing something. Velocity, like momentum, is a vector, and if you don't include this, it throws the entire calculation off. It's a negative. Very good. This guy has to have a negative. So don't forget that energy, you don't have to add it. But for momentum, it's very important that you make sure to include a negative sign anytime an object is left or down. Okay, so it says these two objects collide and stick together. So what type of collision is it? It's a completely inelastic collision, right? So let's find out how much momentum I have before these two objects collide and stick together. So initial momentum of the system is going to be, and I'm using the equation P is equal to, momentum is equal to mv. Okay, so this is going to be 1 times 4. Does everybody agree that that would be the momentum of this guy? Mass times velocity. Plus mass, which is 2, times velocity, which is negative 2. And just like in that other question with the 2 cars colliding head on, look at this. What are we left with? 0. Does everybody agree that when we plug that all into the calculator, we get 0? So when these two objects collide and stick together, what are they going to do?
Stop.
We're going to stop, like this. So therefore, at the end, it's saying how fast are the blocks moving? The answer would be C. They're going to be at rest after they stick together. Because the initial momentum of the system has to be 0, so when they finally stick together, they have to stop. Okay, now finally number 10. Take a look at number 10. Number 10 says a skier is gliding down a gentle slope. So here's a skier going down a gentle slope. Okay. So as the skier goes downhill, question for you, what happens to altitude? Altitude decreases, so therefore what happens to potential energy?
Decreases.
Decreases. Now usually we're used to situations where if the potential decreases, kinetic has got to increase, right? Like if I drop this pen, as it falls it accelerates. It picks up kinetic energy. Gravity's doing positive work, right? So we're losing potential because gravity's doing positive work, and therefore the kinetic energy of the pen increases. But in this case, it says that the skier goes down the hill at a constant speed. So we're losing potential energy, but none of that lost potential energy is turning into kinetic energy. So what's the only explanation for this?
Friction.
If we cannot allow energy to be created or destroyed, so what do?
Friction.
Friction. There's friction. Does everybody agree there has to be friction for this to happen? And what does friction do? It's going to dissipate that amount of energy, the amount of potential energy that I lose. It's going to dissipate it in the form of thermal energy or heat energy. So in this situation, this is a transformation of energy from gravitational potential energy not into kinetic energy, which would be, if there was friction, in a frictionless case, this would be into E sub TH. TH stands for thermal, and E is energy. So this would be thermal energy or heat energy that's being generated out of the lost potential energy. So the answer to this one would be D. It's a transformation from potential energy to thermal energy. Okay, so any questions from the exam or any other questions that you want to ask me?
How do you incorporate integrate friction into the problem?
Friction into the problem, you would have to use the equation. We did a problem like that. It was the one where it was U initial plus K initial plus work non-conservative. And the work non-conservative is the work done by friction. Okay, we did that example. And that's equal to U final plus K final. So in order to incorporate friction, you would have to do everything the same that you would normally do, except you would have to calculate the work done by friction during that process. That's it. Yeah. Yep.
I have a quick question for number 13 on chapter 10.